Hello students. So today we are going to discuss magnetism and matter NCERT exercise. So let's begin. So this is the disclaimer. The learning objectives. So after this lecture, you are going to understand or you are able to calculate the magnetic moment of a bar magnet when given the torque experienced in a uniform magnetic field. Understand and determine stable and unstable equilibrium positions of a bar magnet in a uniform magnetic field. Analyze the behavior of a solenoid as a bar magnet and calculate its magnetic moment using number of turns, area, and current. And you will be able to solve problems involving work done and torque on magnetic dipoles when rotated in uniform magnetic fields. You will be able to calculate magnetic field strength at various position axial or equatorial lines around a bar magnet using its magnetic moment. So the topics that we are going to discuss today is NCERT exercise. There are total 7 NCERT exercise questions in chapter magnetism and matter. And in this lecture, we are going to cover all the questions 5.1 to 5.7. So let's begin with first NCERT exercise 5.1. So question is, a short bar magnet placed with its axis at 30 degree with a uniform external magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 to the power minus 2 joule. Okay, so torque is given and magnetic field is given, and the angle between the dipole moment and the magnetic field is given 30 degree. So what is the magnitude of magnetic moment? That thing you have to find. So I will give you some time to solve it. So you should solve the question and write the answer in the chat box. Okay, and after I will move on to the solution, you can verify your answer. So let's see solution. So using concept 19.7, magnetic field strength is given, which is 0.25 Tesla. And torque on the bar magnet is given, tau is equal to 4.5 into 10 to the power minus 2 joule. Okay, so first we have to list all the things given in the question. Okay, then it will be easy to solve the question, or it will be easy to understand that what formula is going to apply here. Okay, so angle between the bar magnet and external field is also given, theta equal to 30 degree. So torque is related to the magnetic moment as tau is given by m vector, that is dipole moment vector, cross magnetic field vector. Okay, NCERT equation 5.2. But we have to calculate the magnitude of magnetic moment, so we will take this equation as in the terms of magnitude. So in terms of magnitude, the equation is given by tau is equal to mb sine theta. Okay, theta is the angle between the magnetic moment, direction of magnetic moment, and direction of magnetic field, where theta is the angle between external magnetic field and magnetic moment of bar magnet. So magnitude of magnetic moment is given by, so after rearranging this equation, it will become tau upon b sine theta. So m will be equal to tau upon b sine theta. So after, now we will substitute all the values given in the question and we will find the magnitude of magnetic moment. So after substituting all the values, m equal to 4.5 into 10 to the power minus 2 upon 0.25 into sine 30 degree. Okay, sine 30 degree, we know that sine 30 degree is 1 by 2. So m will be equal to 4.5 into 10 to the power minus 2 upon 0.25 into 1 by 2. Okay, so this 2 will go in the numerator. So 4.5 into 2 will become 9. And after removing the decimal from this 0.25, 100 will go in the numerator. So 9 into 100 will become 900. Or in the denominator, it will be only 25 left. Okay, so m is equal to 900 into 10 raised to the minus 2 upon 25. Okay, now 900 by 25, 25 into 400, and 4 into 9, 36. Okay, so m will be equal to 36 into 10 raised to the minus 2 joule per Tesla. Okay, so unit of torque is Newton meter, or we can say joule also. Okay, so joule upon magnetic field, that is Tesla. Okay, we can write SI unit as Newton meter per Tesla also. Okay, but joule per Tesla is also correct unit. So magnitude of magnetic moment of bar magnet is 36 into 10 raised to the minus 2 joule per Tesla. Okay. Okay, so next question. A short bar magnet of magnetic moment M is equal to 0.32 joule per Tesla. Okay, magnetic moment is given. Is placed in uniform magnetic field 0.15 Tesla if the bar is free to rotate in the plane of the field. Which orientation would correspond to it? Stable, and B part is unstable equilibrium. Okay, so bar is free to rotate, and magnitude of magnetic moment is given, and magnetic field is also given. Okay, so bar is free to rotate. So which, at what orientation, or we can say theta. So what will be the theta for stable equilibrium or for unstable equilibrium? So what is the potential energy of the magnet in this case? So I will give you some time to solve it. So let's see the solution using concept 19.6. Moment of the bar magnet M is given by 0.32 joule per Tesla. External magnetic field B is equal to 0.15 Tesla. Potential energy of the bar magnet is given by, so we know that potential energy of bar magnet, we have derived the relation, which is UM, magnetic potential energy, will be equal to minus M vector dot B vector. It is negative of dot product of magnetic moment and magnetic field vector. Okay, NCERT equation 5.3. And magnitude of this it is a scalar quantity, so it will not be having direction, or this dot product will result in scalar quantity. So magnetic potential energy will be equal to minus dot product will result in MB cos theta. Theta is the angle between this magnetic moment vector and this magnetic field, where theta is the angle between magnetic field and magnetic moment of bar magnet. So figure showing different equilibrium positions. So now we will display a figure which will be showing different equilibrium positions, stable and unstable, and also non-equilibrium position of a bar magnet in external field. So this is the figure. So for this orientation, where magnetic moment is having same direction as magnetic field, okay, then theta will be equal to 0. And we know that torque is equal to, magnitude of torque is MB sine theta. So sine 0. Okay, so we are not dealing with torque in this question, but I will explain this also. Okay, torque will be MB sine theta. Theta is 0, so sine 0 is 0. So torque will be 0 and torque minimum in this condition. But magnetic field is minus MB cos theta, and theta is 0, cos 0 is 1. So magnetic potential energy will be minus mb. So it is least negative, most negative value of the magnetic potential energy. So means minimum value of potential energy. That means stable position. Okay. So the position at which potential energy is minimum is known as stable position. Okay. And in this orientation, theta is pi by 2. So torque is mb sine theta. Sine pi by 2 is 1. So torque will be having maximum value, tau max mb. But cos pi by 2 is 0. So potential energy will be 0 at this orientation. We have also taken the reference. We have taken this orientation as reference for potential energy in the derivation, where theta equal to pi by 2 and potential energy becomes 0. So we have taken a reference here. Okay. And another orientation where magnetic moment is oriented in the opposite direction. So magnetic moment will be having opposite direction as magnetic field. So theta equal to pi and torque is sine 0 is 0, sine pi is also 0. So sine pi will be 0. So torque will be minimum at this orientation also. At this orientation and at this orientation, torque will be 0, minimum value. But potential energy is minus mb cos theta. So cos 0 is 1, cos pi is minus 1. Okay. So here minus mb minus 1. So it will result in mb, positive mb. So potential energy will be most positive here, means maximum value of potential energy, that is mb. So it is also equilibrium position, but what equilibrium? Unstable equilibrium. Okay. So these are three orientation and showing stable, unstable and non-equilibrium condition. So potential energy um is minimum when theta equal to 0, that is called stable equilibrium, and maximum when theta equal to pi, which is unstable equilibrium. For stable equilibrium, theta is equal to 0. Potential energy of the system will be equal to minus mb cos 0 degree, that is minus mb, because cos 0 degree is 1. So given m value of m is 0.32 and b is 0.15. So these are only values I am giving. Okay. So put these values in this. So will be equal to minus 0.32 into 0.15. So will be equal to minus 4.8 into 10 to the power minus 2 joule, because it is potential energy, unit will be joule. Okay. I have not written units here because I am only writing the values that we are going to put in the equation. So m is equal to 0.32. This is the only value, quantity. For unstable equilibrium, theta equal to 180 degree. Potential energy of the system is equal to equal to minus mb cos 180 degree. So cos 180 degree is minus 1. So it will result in mb. So at unstable equilibrium, m and b is given, quantities of m and b is given, and will be equal to 0.32 into 0.15, and it will result in 4.8 into 10 to the power minus 2 joule. Got it? So potential energy at stable equilibrium is minus 4.8 into 10 to the power minus 2 joule, and at unstable equilibrium, it is 4.8 into 10 to the power minus joule. Okay, you can see quantity is same, but there is a negative sign. It is minimum potential energy, it is maximum potential energy. Got it? Okay, next question, exercise 5.3. A closely wound solenoid of 800 turns. Okay, n is given, capital N is given, and area of cross section 2.5 into 10 to the power minus 4 meter square. A is given and carries a current 3.0 A ampere. Okay, current I is given 3 ampere, capital N is given 800 turns, and A is given 2.5 into 10 to the power minus 4 meter square. Explain the sense in which the solenoid acts like a bar magnet. What is its associated magnetic moment? Okay, we have to calculate the magnetic moment and explain the sense in which the solenoid acts as a bar magnet. Okay, so I will give you some time to solve it. Using concept 18.12, number of turns in the solenoid is given n equal to 800, and area of cross section is given A equal to 2.5 into 10 to the minus 4 meter square. Current in the solenoid is given I equal to 3 ampere. Okay. So this is the diagram showing that how pattern of solenoid resembles the pattern of magnetic field lines in the bar magnet. Okay, we have also discussed it. That pattern is similar in both cases. So figure 5.2 A and B. Figure 5.2a shows magnetic field lines due to a bar magnet. Okay, in A diagram, it is bar magnet. And figure 5.2b shows magnetic field lines due to a solenoid. So you can see pattern is similar. So current carrying solenoid behave as a bar magnet because pattern of magnetic field lines for both is similar. One end of solenoid act as a north pole and other as a south pole. We know that for a bar magnet, there is two poles, north and south. Also for a solenoid, one end acts as a north pole and other as a south pole. Okay, so how can we determine which pole is north and south? So you can see the end of the oil coil from a side. From that end, you are seeing the one end of the solenoid. Okay, if at the end of the solenoid the current is in clockwise direction, then it is south pole. If current is in anti-clockwise direction, then it is north pole. Okay, we can determine the poles also, or we can find it by using the direction of magnetic field at that end using right hand thumb rule also. Okay, now we are going to calculate its associated magnetic moment. So magnetic moment due to current carrying loop having n turns. Okay, so for one current carrying loop, magnetic moment is current into area of the loop, I into A. But solenoid we can consider as a closely wound solenoid, we can consider as a number of n number of circular loops. Okay, so for one loop magnetic moment is IA. For n number of turns, magnetic moment is NIA. Okay, so we are going to multiply it with n turns. Okay, solenoid is closely wound, so every winding can be considered as a loop. So for one loop, magnetic moment is IA. For number of n number of loops, which is in 800 turns in the solenoid, so capital N will be 800. So we are going to multiply this 800 with the magnetic moment of one loop. Okay, so M equal to NIA, NCERT equation 4.24. So current is given 3 ampere, N is given 800 turns, and area is given 2.5 into 10 to the minus 4 meter square. Okay, so after putting these values, we will get M equal to 800 into 3 into 2.5 into 10 to the power minus 4. Okay, after solving it, M equal to 2400, 800 into 3 into 2.5 into 10 to the power minus 4. M will be equal to 2400 into 2.5 results in 6000 into 10 to the power minus 4. So it will result in 0.6 joule per Tesla. Okay, this is the unit of magnetic moment. So associated magnetic moment for given bar magnet is 0.6 joule per Tesla. Got it? Okay, now exercise 5.4. If a solenoid in exercise 5.3, now we are taking reference of 5.3, that's why we have also written 5.3 exercise statement again. So if the solenoid in exercise 5.3 is free to turn about the vertical direction, okay, solenoid is free to turn about the vertical direction, and a uniform horizontal magnetic field of 0.25 Tesla is applied. What is the magnitude of torque? Now we are considering this solenoid as a dipole. We can consider this solenoid as a bar magnet, as in the case of bar magnet in the uniform magnetic field. We are considering here now solenoid in the uniform magnetic field, uniform horizontal magnetic field of 0.25 Tesla. And this solenoid is free to turn about a vertical direction. What is the magnitude of a torque on the solenoid when its axis makes an angle 30 degree with the direction of applied field? Okay, angle is also given. Now what was the exercise 5.3? Closely wound solenoid of 800 tons and area of cross section 2.5 into 10 power minus 4 meter square carries a turn 3 ampere. Explain the sense in which solenoid acts as a bar magnet and what is its associated magnetic moment. Okay, to find the torque, we have to we should know the magnetic moment that we have calculated in previous exercise 5.3. Okay, that's why we are taking the reference, and theta is given and magnetic field is also given, so we have to calculate the torque. So I will give you some time to think about it. Okay, solution using concept 19.7. Magnetic field strength is given B equal to 0.25 Tesla. Magnetic moment of solenoid that we have found in exercise 5.3 in previous exercise, M is given by 0.6 joule per Tesla. And angle theta is also given between the axis of solenoid and direction of the applied field is 30 degree. Okay, all the values are given. So torque acting on the solenoid is given by tau is equal to m vector cross b vector, NCERT equation 5.2. And in terms of magnitude, because we have to calculate the magnitude of torque. So in terms of magnitude, it will be mb sine theta. We are not considering direction. Okay, because we don't know the direction of magnetic moment in a solenoid. Okay, we don't know in which direction north pole is there, in which direction south pole is there. We don't know the direction of current flowing through the solenoid. So we cannot determine the direction of torque without knowing the direction of current and the poles of the solenoid. Okay, that's why we are only calculating the torque. So given m equal to 0.6 and b equal to 0.25 Tesla. So tau is given by 0.6 into 0.25 into sine 30 degree. Okay, mb sine 30 degree. And this sine 30 degree is 1 by 2. And 0.6 into 0.25 will become 0.15. So tau will be equal to 7.5 into 10 to the power minus 2 joule. So magnitude of the torque on the solenoid in this case is 7.5 into 10 to the power minus 2 joule. Okay. Now next question. Exercise 5.5. A bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of uniform magnetic field of 0.22 Tesla. So A part of this question is, what is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field direction and opposite to the field direction. Okay, since bar magnet is aligned in the direction of magnetic field, means it is in stable equilibrium. So to disturb its equilibrium position, we have to do the external work. Okay, so we have to do the external work against the torque. Okay, so work required by the external torque. That external torque we are applying against the torque that is being applied due to the magnetic field. Okay, so we are doing external work to rotate this magnet from its equilibrium position to first part normal. We are aligning it to normal to the field direction or then opposite to the field direction. These are the two cases. And B part is, what is the torque on these positions? In case 1, normal to the field direction, and what is the torque when it is opposite to the field direction? Okay, so This question can be divided into two parts, A and B. And in A and B, there are also two cases. So I will give you some time to solve it or think about it. Let's see a solution. Using concept 19.6 and 19.7, magnetic moment is given by 1.5 joule per Tesla and magnetic field strength B equal to 0.22 Tesla. Then net amount of work done on bar magnet by external agent. So we are doing external work or we are applying the external torque to rotate the magnet. So then amount of work done on the bar magnet by external agent, work external, is equal to the change in potential energy of the bar magnet. Okay, we are changing its potential energy. So it will be change in potential energy will be equal to the external work. So work external will be change in potential energy, final potential energy minus initial potential energy. Okay, so these final and initial potential energy are with respect to reference. So with respect to reference, magnetic potential energy we have defined or derived. So potential energy of bar magnet in presence of external field is given by at some particular orientation. So um is equal to minus m vector dot b vector, which is equal to minus mb cos theta. So at particular theta, okay, magnetic particular orientation, particular theta, magnetic potential energy can be found using this formula. So we have to find the UF, that is final magnetic potential energy, and UI, initial magnetic potential energy. Then we have to take the difference. It will give us the work external. So in A part, first part. In A part, there is a sub part, first part. So first part, when magnetic moment is aligned normal to the field direction. So then initial angle, what was the initial alignment? Magnetic moment was aligned parallel to the or aligned in the direction of magnetic field. That means theta 1 equal to 0 degree. Initial angle between the magnetic moment and magnetic field is theta 1 0 degree. And final angle when it is rotated and its orientation is now normal to the field direction. Okay, so final angle between the magnetic moment and magnetic field direction is now theta 2 equal to 90 degree. Then work done by external agent is given by work external change in potential energy. Okay, so potential energy at one orientation is given by minus mb cos theta. Okay, so final energy when it is rotated through some angle and it is normal to the field direction. So theta 2 is 90 degree. So final energy will be minus mb cos theta 2 and initial energy will be minus mb cos theta 1. Okay, so we have taken the difference uf minus ui. Okay, so minus mb cos theta minus and minus again. So it will become plus minus mb cos theta 1. So we have taken minus mb as common. So it will result in bracket, it is cos theta 2 minus cos theta 1. Understood? Delta u is equal to uf minus ui. So uf is minus mb cos theta 2. Ui is minus mb cos theta 1. So taking the difference of 2 and taking minus mb common, so it will result in minus mb cos theta 2 minus cos theta 1. Okay, now we will put the values. So given B equal to 0.22 Tesla, M equal to 1.5 Joule per Tesla, and cos 0 degree is 1, cos 90 degree is 0. Theta 1 is 0 degree and theta 2 is 90 degree. Okay, so we have taken the value. So W1 means in the first case when magnetic moment is normal to the field direction. So W1 will be equal to minus 1.5. That 1.5 is M and 0.22 that is B in bracket cos theta 2 that is 90 degree minus theta 1. So cos 0 degree. Okay, so cos 90 degree is 0. So 0 minus cos 0 degree is 1. So 0 minus 1 in bracket and 1.5 into 0.22 will result in minus 0.33. Okay, so multiplying this, external work will be, Wi will be 0.33 joule. So this is the external work done to rotate the magnet through 90 degree angle. And from the position where it is aligned with the magnetic field to the position when it is normal to the field direction. Okay, now in A part there is a second sub part. So we are going to do that now. Initial angle between the magnetic moment and magnetic field is given theta 1 equal to 0 degree. Now final angle will be, we are rotating the bar magnet from its equilibrium, stable equilibrium position to unstable equilibrium position. We are aligning the magnetic moment in the opposite direction of field. Initially it is in the direction of field. Now we are rotating the magnet and aligning magnetic moment in the opposite direction of field. So theta 2 will be 180 degree. Okay, then the work done by external agent is given by, work external is minus MB cos theta 2 minus cos theta 1. Okay. So B is given 0.22 Tesla, M is given 1.5 Joule per Tesla, cos 0 degree is 1 and cos 180 degrees minus 1. Okay, so work second subpart, work second is equal to minus 1.5 into 0.22 cos 180 minus cos 0 degree. Okay, so cos work done in second case when magnetic moment is aligned in the opposite direction of the field is minus 0.33 and cos 180 degrees minus 1, cos 0 degrees also minus 1. Oh, sorry, 1. And minus is in the formula. So this minus will remain as it is. Cos 0 degrees 1, cos 180 degrees minus 1. So minus 1, minus 2. So this minus and this minus 2 minus from here will cancel out. So 0.33 into 2, it will result in work in second part is 0.66 joule. So work done to rotate the bar magnet from its stable equilibrium position to unstable equilibrium position is 0.66 joule. Okay, now a bar magnet, okay, same question and B part. What is the torque on the magnet in cases 1 and 2? And now in first case, now torque on the alignment or orientation in first case and second case. First case orientation is magnetic moment is at 90 degree angle with the direction of uniform magnetic field. So theta will be 90 degree in first case and theta will be 180 degree in the second case because magnetic moment is in the opposite direction to the field direction. So we can calculate the torque. So to find the torque on the magnet, torque on magnet in presence of external magnetic field is given by tau is equal to m cross b. Okay, so in terms of magnitude we can say tau is equal to mb sin theta, where theta is the angle between external magnetic field and magnetic moment of the magnet. Now in B part first case, for case 1 theta equal to 90 degree. So torque will be given as tau 1 in first case. Torque in first case will be equal to mb sin theta. mb sin theta is 90 degree in first case. So tau first will be equal to 1.5 into 10 into 0.22 into 1. Sin 90 degree is 1. So tau first will be equal to 0.33 joule. So this is the torque acting on this case when magnetic moment is perpendicular to the field direction. Now, second case, when theta is equal to 180 degree, torque is given by tau second in second part, mb sine theta, and theta is 180 degree because magnetic moment is in opposite direction to the field. And tau second is equal to mb into, because sine 180 degree is 0, so mb into 0, so torque in second case will be 0. So no torque is acting when magnetic moment is aligned in the opposite direction or in the same direction. We have seen in the diagram also. There are two cases when torque is 0, minimum torque, when magnetic moment is aligned in the direction of magnetic field, and when magnetic moment is aligned in the opposite direction of magnetic field. In both cases, torque will be minimum, which is equal to 0. Okay, so next question. A closely wound solenoid of 2000 turns and area of cross section 1.6 into 10 to the power minus 4 meter square, carrying a current of 4 ampere. Okay, area is given, current is given, and number of turns 2000 is also given. Is suspended through its center. Okay, it is suspended, it is connected through its end and suspended freely and allowing it to turn in a horizontal plane. What is the A part? What is the magnetic moment associated with the solenoid? We have calculated this type of question previously also. So it will be, what is the magnetic moment for one loop is IA. What is magnetic moment for a loop containing number of turns? Solenoid is a type of loop also containing closely wound 2000 turns. Okay, so multiply by 2000. So what is the force and torque on the solenoid if uniform horizontal magnetic field of 7.5 into 10 to the power minus 2 Tesla is set up at an angle of 30 degree? Okay, if magnetic field is there, which and its magnitude is 7.5 into 10 to the power minus 2 Tesla, an angle between the magnetic moment and solenoid is given 30 degree. So what is the force and torque on the solenoid? So we have calculated this. So I will give you some time to think about it. So let's see the solution. Using concept 18.12 and 19.7. Number of turns on the solenoid n equal to 2000. It is given. Area of cross section of the solenoid is also given. A equal to 1.6 into 10 to the power minus 4 meter square. Current in the solenoid is given. I equal to 4 ampere. Now A part. Magnetic moment M due to current carrying circular loop having n turns is given by M equal to NIA. NCERT equation 4.24. Okay. So magnetic moment we can calculate easily after putting the values. N is given, A is given, and I is given. After substituting all the values, you will get M equal to 2000, that is number of turns, into 4, that is current, and into area of cross section 1.6 into 10 to the power minus 4. Okay. So after solving it, magnetic moment will be M equal to 1.28 ampere meter square. So magnetic moment of solenoid is 1.28 ampere meter square. Got it? Now A part is finished. B part. B part, when magnetic field is uniform. Okay, we have derived the relation. We have derived this thing for the bar magnet. When bar magnet is placed inside a uniform magnetic field. So net force on the bar magnet is zero. So solid pattern of magnetic field lines is similar to the bar magnet. Okay, and it resembles closely wound solenoid of same measurements, resembles the bar magnet. So when it is suspended freely inside a horizontal uniform magnetic field, then net force on it is will be also net force on the solenoid will also be zero here. Okay, so in if magnetic field is uniform, then for net force on the solenoid will be zero, but net torque on the bar magnet is not zero. But like we have seen, net torque on the bar magnet is not zero. Okay, so net torque on the solenoid will also be non-zero. Okay, solenoid and bar magnet are equivalent. Since the forces acting on two ends of a solenoid have different lines of action, because forces that are acting on two different ends of the solenoid or bar magnet, okay, they have different lines of action. They are not acting on same line of action. Okay, so they are, net force is zero, but net torque is not zero. They will produce a couple. They tends to rotate the solenoid or bar magnet. Okay, so net torque will be there. So magnetic field B is equal to 7.5 into 10 to the power minus 2 Tesla. So magnitude of torque is given by tau is equal to mb sin theta, NCERT equation 5.2. So we are concerned about magnitude only. Okay. Now angle between the magnetic field and axis of the solenoid is given also 30 degree. So tau torque will be tau equal to 1.28 into 7.5 into 10 to the power minus 2 into 1 by 2, because sine 30 degree is 1 by 2. And torque, magnitude of torque is 4.8 into 10 to the power minus 2 Newton meter. So torque on the solenoid is 4.8 into 10 to the power minus 2 Newton meter. Okay, so no force is acting on the solenoid, but torque is acting on the solenoid. Okay, similar case. It is similar to bar magnet. Okay, so last question. A short bar magnet has a magnetic moment of 0.48 joule per Tesla. Give the direction and magnitude of the magnetic field produced by the magnet at a distance 10 centimeter from the center of the magnet. Okay, so we are taking a magnetic dipole here. Short bar magnet. That is the case of short magnetic dipole, as we have done for short electric dipole also. Okay, so we have draw the analogous in the theory section also. Okay, so that is based on that concept. So short bar magnet, short magnetic dipole moment. Okay, so having dipole moment 0.48 joule per Tesla, and we can neglect the length of the dipole as compared to the distance r, that is given 10 centimeter. Distance r is from center of the dipole to the point where we are going to find the magnetic field. Okay, we can neglect because bar magnet is so short. Okay, so give the direction and magnitude of magnetic field by the magnet at a distance of 10 centimeter from the center of the magnet. A part is on the axis, that means axial line, and B part is the equatorial lines. That is the case of equatorial line, and A part is the case of axial line. Equatorial line mean normal bisector. A line passing through center of the dipole and perpendicular to it of the magnet. So I will give you some time to think about it. Okay, let's see the solution. Using concept 19.2 and 19.3, magnetic moment of bar magnet is given B m equal to 0.48 joule per Tesla. distance D is equal to 10 centimeter equal to 0.1 meter. And A part, on the actual line, on the axis, magnitude of magnetic field at a distance r from the center of the magnet on the axis is given by, on the axial line is given by the relation B equal to mu naught by 4 pi 2m by r cube. This is the magnetic field at axial line at a distance r from the short dipole. Okay, short dipole, or we can say that r is much greater than the length of the dipole. NCERT question 5.1. Okay, where mu naught is permeability of free space, which is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. Substituting values of m and r in the equation, so B will be equal to 4 pi into 10 to the power minus 7 into 2 into 0.48 upon 4 pi into 10 to the power, or we can say 0.1 raised to power 3, or we can say 10 to the power minus 3. Okay, so 4 pi and 4 pi will get cancelled out. Okay, and this 2 into 0.48 will become 9.6, 0.96, and this 0.1 raised to power 3 will become 10 to the power minus 3. Okay, so B will be equal to 10 to the power minus 7 into 0.96 upon 10 to the power minus 3. So after solving it, magnetic field will be equal to 0.96 into 10 to the power minus 4 Tesla. Okay, so now we are going to calculate the magnetic field at the equatorial line. We know that formula for equatorial line is, magnetic field at equatorial line is half of the magnetic field at axial line if distance r is same. Okay, so distance r is same in the both cases, 10 centimeter. So B will be 0.48. You can calculate, or you can determine the magnetic field at the equatorial line directly by taking half of the magnetic field as compared to axial line if distances r is same for both, or you can solve it separately. So we know that 1 Tesla is equal to 10 to the power minus 4 Gauss. Okay, this is the CGS unit. Gauss is a CGS unit. So 1 Tesla contains 10 to the power minus 4 Gauss. So this results can also be written as B equal to 0.96 Gauss. So this is a CGS unit, Gauss. So 1 Tesla is equal to 10 to the power minus 4 Gauss. So B equal to 0.96 Gauss. This magnetic field is along the direction of magnetic dipole moment of bar magnet. Okay, on the axis, the direction of magnetic field line is along the magnetic moment, that is from south to north, is along the magnetic moment direction. Okay, so this magnetic field is along the direction of magnetic dipole moment of the bar magnet. It means that direction of magnetic field is from south pole to north pole of the bar magnet. Got it? Now for equatorial line, B part, magnitude of magnetic field at a distance r on the equatorial line of the magnet is given as B equal to mu naught m upon 4 pi r cube, which is half of the magnetic field as compared to the axial line for same distance r. NCERT question 5.4, where mu naught is the permeability of free space, which is given by 4 pi into 10 to the power minus 7 Tesla meter per ampere. Substituting values of m and r here, you will get B equal to 4 pi into 10 to the power minus 7 into 0.48 upon 4 pi 0.1 raised to power 3. Okay, 4 pi and 4 pi will get cancelled out, and B equal to 10 to the power minus 7 into 0.48 upon 10 to the power minus 3. Okay, so it will result in B equal to 0.48 into 10 to the power minus 4 Tesla. So this is the magnetic field, which is half of the magnetic field at axis, which at axis magnetic field was 0.96 into 10 to the power 4 Tesla. Okay, so in terms of Gauss, we can write B equal to 0.48 Gauss. This magnetic field is along a direction opposite. Now at equatorial line, magnetic field direction is opposite to the magnetic dipole moment. So this magnetic field is along a direction opposite to the magnetic dipole moment of the bar magnet. It means that direction of magnetic field is along north pole to south pole of the bar magnet. Magnetic moment is from south pole to north pole, but magnetic field direction is for equatorial line is opposite. So it will be along north pole to south pole of the bar magnet. Got it? So thank you. This is all about the exercise problems. I hope you enjoyed the session. Thank you.